After presenting series and parallel circuits, well, in reality, we often have circuits that combine elements of series and parallel circuits together, as you can see over here. Here we have a circuit that has two parallel branches connected together in series. So this video is going to look at how we can apply Kirchhoff's laws to a complex circuit like this, how we can calculate the total resistance and the total current, how we can calculate voltage drops across each of those resistors, and in the end, we're going to look at how we can calculate the power in each of these components. So in this circuit, we have a 24-volt battery. We have this parallel branch where you got a 100 ohm resistor and a 250 ohm resistor. We have a 350 ohm resistor and a 200 ohm resistor. So before starting, what could happen? Where could a positive charge fly when it goes to this circuit? Well, it has four different paths it can take. It can go like that. It can go like that. It can go like that. And, I can't even remember the last one. There's another one it can do. It can do four different paths, okay? So that's the problem here, is we have four different paths that charge can go. And as it's going through those paths, it has to apply Kirchhoff's laws. So how do we try to figure out the current or other factors involved in these circuits? Well, when we're applying Kirchhoff's law, the simplest thing that you can do is take a look at it and say, let's take a look at the voltage law, which says that the sum of the potential drops across the circuit has to be equal to the potential of the battery. Okay, so one way I can do this is I can take a look at it and say, well, this really is a series circuit with parallel branches. So what I can do is I can convert these parallel components into a quasi resistor on its own by just using the rules for finding the total resistance of these parallel branches. So for example, for branch A, I could find the total resistance of that component and treat it as just one resistor by using the formula 1 over R total is equal to 1 over 100 ohms plus 1 over 250 ohms. Okay, you can see that here, all right? And then if I do the math, our total for that A component is going to be equal to, I already calculated it before, 71.4 ohms. Okay, so the total resistance of that branch is 71.4 ohms, as if that charge is just going through that entire branch. Okay, and if I do the same process, here for B, where 1 over 350 plus 1 over 200, I get our total for that B branch is going to be equal to 127.3 ohms, okay, for that guy. All right, then this becomes a lot simpler. Then what's going to happen is my potential going across branch B first, my potential going across branch B, based on the way I drew this, is the voltage drop is going to be related to that resistance, which is more than that resistance. So I'm expecting a larger potential drop across there than I will over here. So how would we calculate the potential drop across here? So if you go back to the previous video, I created a simple formula for that where you would say, so the voltage drop is going to be equal to the original voltage times the resistance over R total. Okay, so that fraction of the total resistance. So then that voltage drop is going to be equal to 24 volts times 127.3 ohms divided by around 198 ohms. Okay, a little bit more than that, but in order for us to do that, let's do that in our calculator right now. Okay, so what I would see is 24 times 127.3 divided by 198 gives me 15.4 volts. Okay, so according to Kirchhoff's voltage law, 15.4 volts is going to be going across here. Okay, and to find out how much is going across A, there's two things I can do. I can take 24 minus 15.4, would give me how much it is, or I can apply this same relationship. So either way, so if I took 24 minus 15.4, I can see that the voltage drop here will be 8.6. I just want to confirm it by using that relationship that we have here. So V drop, this was for B and this is for A, is going to be equal to 24 volts times 71.4 ohms divided by 198 ohms. Is equal to 8.7 volts, okay? Or 8.6. 8.6 or 8.7, so probably rounding it. That's just a rounding error. So yeah, so that worked out. So this is 8.6 volts, and this is 15.4 volts. Add those together, and that makes up 24 volts. So according to Kirchhoff's voltage law, okay, I can say that the voltage going across that resistor, so if I had a voltmeter attached here, if I had a voltmeter attached there, okay, for A, that's going to read 8.6 volts. This is going to read 8.6 volts, okay, and if I had a voltmeter attached here, and if I had a voltmeter attached here, this one's going to read 15.4 volts, and that one is also going to read 15.4 volts. Okay, so you're using Kirchhoff's voltage law. I'm able to find out what is the voltage going across each of these resistors. Okay, so just to review, what you do is you treat these parallel branches as individual resistors, and you have to use the rules that we talked about in the last video to calculate the total resistance for these branches. Okay, using that. Once I've calculated the total resistance for those branches, I can treat it as a simple series circuit to find the voltage drops across those branches. Okay, so that's a really, really nice exercise to get you to practice Kirchhoff's law and everything that we used in the last series. Okay, so now that I found the voltages across each of those resistors, I can then move on and do things like calculate the current or the power that's happening here. So let's take a look for the current law. The current law says that the sum of the current going in is equal to the sum of the current going out. So whatever the current is going through here, okay, so here's a junction. So the current going through here plus the current going through here is going to be the sum current, which is going to be equal to the current going here and the current going here. So without getting overly complicated, what I can do to find the total current, if I had an ammeter here, to find the total current going through there, okay, the total current, oops, let's change the color here. Okay, so if I wanted to find the total current, okay, it's going to be the total voltage divided by the total resistance, okay, which we calculated in the previous, okay, in the previous thing here, we calculated the total resistance is 198 ohms. So I'd be able to calculate the total current by taking 24 volts divided by 198 ohms. Now just pay attention here that 198 ohms is less than some of the resistors in this circuit. And that's just because of the parallel properties here. When I have resistors in parallel, the overall resistance is less than the resistance of each individual component, right? So the total resistance in this circuit is actually less than 3 of the resistors that are in there. That's just because they've been connected in parallel, okay? So 24 volts divided by 198 would give me my total current. So if I put that through the calculator, okay, 24 divided by 198 gives me 0.12 amps. Okay, that would allow me to calculate the total current. But if I wanted to find the current in each of these branches, how would I do that? So in order to find the current in each of these branches, I had my voltages. Okay, so you had your voltages from the previous voltage law. So for example, 8.6 volts is here, and that's my 100 ohm resistor. So I could find the current in that branch by taking the voltage divided by the resistance. Okay, so that would give me the current here. This voltage divided by that resistance would give me the current here. Okay, so what I'm asking here is if I had ammeters, let's say I had ammeters, sorry, these are small circles, but if I had ammeters on every single branch, I would be able to calculate what those ammeters would be reading. Okay, so that ammeter would say 8.6 volts divided by 100. Okay, so that's going to be 0.086 amps. Okay, and this is going to be 8.6 volt divided by 250, which is going to be a lot less. And those two currents added together should always equal to 0.12 amps. So 0.12 amps is going to be going in here, coming out here. 0.12 amps is going to be coming in here at this junction, and 0.12 amps should be coming out there. So the voltage here, which was 15.4 volts, okay, 15.4 volts divided by 350, 15.4 volts divided by 200, that'll tell me the currents here, and those two currents added together should equal to 0.12 amps, okay? So solving for the voltages across each resistor is what we actually did up here. To solve for the voltage across each resistor, okay, I needed to then create this drawing, okay, and then solve for the total resistance of each branch, and then apply these formulas to calculate the voltage drop across each resistor, okay? And if I wanted to just look at this circuit and solve for the total resistance, which is what we did before, again, the total resistance I would have to do for this guy, just to remind you, 1 over R total is equal to 1 over R1 plus 1 over R2. Okay, to solve for the total resistance of that branch, 1 over R total is equal to 1 over R3 plus 1 over R4. And then R total for the entire circuit is going to be, let's call that A, let's call that B. It's going to be the resistance of A plus the resistance of B, okay? So just remember, all you're doing is you're distilling this. You're taking that parallel branch, finding the total resistance of that parallel branch, finding the total resistance of that parallel branch, and then you're adding them together, okay? And to solve for the total current, we just did that over here. You take your total voltage divided by the total resistance. That'll give you your total current, okay? And then to solve for power, it's the same thing. So remember, I've given you the formula power is equal to IV, or V squared over R, or I squared times R. You can choose to use any of these. So if I want the total power of the circuit, I know the current. Okay, so power is going to be equal to 0.12 amperes times 24 volts, and that'll give me the total power. Okay, or if I want to find the power in each of these branches, I know the voltage going through that. So voltage squared divided by that particular branch would give me the power in each branch, and they should all add up. All these components, the power going through each of these should give me my power total.